In this next series of videos, we're going to go through how one actually goes out and measures a partial molar quantity at a specific composition. Okay? And so as I've mentioned, or at least sketched before previously, if you take a look at the delta V mix and the delta H mix of a solution that's not ideal, so a non-ideal solution, you'll see that these delta mixes have a parabolic-like shape. And to show you an example of this, your textbook actually has some clear data of this phenomena. Okay, and so on the left-hand side here, we're looking at the delta V mix, or delta molar volume mix of a solution in which you have methylformate mixed with either methanol or ethanol. I believe the methanol curve is this one, and the ethanol curve is this one. But you can see in both cases they have a parabolic shape, where the extreme of this curve is around a mole fraction of 0.5 for both, right? And so you could see, if these were ideal solutions, you would get a value that's just equal to 0 the entire time. But the fact that we have these strong parabola shapes tells us that these solutions are very non-ideal. Okay. Similarly, if we take a look on the right here, we have mixtures of benzene mixed with aromatic fluorocarbons, where they're made up of carbons, fluorines, and some other atom. And we see for all these mixtures, we also get very steep parabolic shapes as well. And so if these mixtures were ideal solutions, the enthalpy would have been 0. But in a lot of cases, we either see that a lot of enthalpy is released from the system as heat, or we can even see a complete sign change as a function of the chemical structure. Okay? And so, at least looking at these data, what one would want to figure out is, okay, if we're at any point along these curves, we know that the species in this mixture, they have some sort of effective volume, their partial molar quantity, or they have some effective enthalpy as well that leads to these sort of parabolic shapes. And so what we're going to look at in these series of videos is we're going to look at how using these delta M mixed data, or if we had some sort of analytical model to describe a delta M mix. So let's say we fit those curves to like a polynomial or something. What we could do is we could then determine the partial molar quantity at that specific mole fraction value. Okay? All right. And so to do this, there's two main methods. So two traditional methods for determining the partial molar quantities. The first method is a graphical method, and the second method is where you use an analytical equation. And so first we're going to start with the graphical method. All right, and so to go through this example, what I want you to consider is the mixing of species 1 and 2 at constant temperature and pressure. Okay, and so let's say on the left-hand side here, you had some species 1 with N1 moles and some pure molar volume, and then you added in some species 2 with N2 moles and V2 molar volume. Okay, and then together those formed a mixture with N1 moles of species 1 and 2 moles of species 2, and then partial molar volumes of species 1 and 2. Okay? All right, at least the way to picture this mathematically, you could say that the math represented here on the left-hand side is describing some sort of ideal solution. But in the right, and so that's why you have the pure molar components here. Now on the right-hand side, what you actually have is your actual mixture, your actual non-ideal mixture, in which the partial molar volumes of each of the species are represented by these V bar things. Okay? All right, and so if we took a look at the change in the total volume of the mixture, once again, that's just V of the actual mixture minus V of the ideal solution, or predicted by the ideal solution, so ID. Okay. We know from our discussions before that the volume of the actual mixture, which is just two components, is equal to Ni times Vi bar, and that for the ideal solution is Ni Vi squiggly. Okay? If we expand out these summations, what we get is N1 V1 bar plus N2 V2 bar minus N1 V squiggly plus N2 V2 squiggly. What I'm then going to do is I'm going to factor out N total from the entire right-hand side, and so that will just convert all these things to mole fractions. Delta V mix equals N, and since we have two components, I'm going to write these in terms of just the mole fraction of the second component. And the reason I'm doing that is a math reason, and that will come up later. Okay, so then minus N, that's x2, v1 hat, plus x2, v2 tilde. I'm now going to combine like terms. So things multiplied by 1 minus x2, I'm going to combine, and things only multiplied by x2, I'm going to combine. I'm also going to divide both sides by n to turn this into the molar volume. So what we have is 1 minus x2, 1 plus x2 v2 minus v2 squiggly. Okay? Alright, so we have an equation, but in our equation we have two unknowns still. v1 and v2 bar. Everything else is something that we could actually either get from measurements or something. So like this delta V mix, this is something that we measure. That's what the data are on this right-hand side. The pure molar volumes for the pure species 1 and species 2, that's something we could just look up, and that's something we would know just from the pure species systems. And then x2, that's just, we need some prior knowledge of the composition of our system. But let's say that's something we have. But the molar volumes, that's something we're trying to determine. And so we have two unknowns right now, and so that means we need another equation in order to determine all those unknowns. All right? And so to get that other equation, what we're going to do is we're actually just going to take the derivative of delta V mix. With respect to x2, because that's the independent variable that we have there now. dx2 delta V mix. We take the derivative get is V1 bar, and with squiggly, V2 bar minus V2 squiggly. And so essentially I just took the derivatives with respect to x2 of these things first, and now I'm going to take the derivative of the stuff inside the parentheses and brackets. These are constants, right? These are the pure values, so they're not functions of x2. And so what we get is 1 minus x2 dv1 dx2 plus x2 dv2 dx2. Okay? Alright, so in this derivative right now we have somewhat of a long equation. But for these terms in the back here, we actually don't need to worry about them, because what we could do is we could go back to our Gibbs-Duhem relationship, which told us that at constant temperature and pressure, the sum of xi times dm property I, that sum is just equal to 0. And that's essentially what we have here, right? 1 minus x2 is x1. So we have x1 dv1 plus x2 dv2. And, we just divided both sides by dx2. But 0 divided by dx2 is also still 0. In any case, from this thermodynamic constraint, we could actually just chop off that part of the equation. And so we get that our derivative is just dx2 delta V mix equals V1 bar minus V squiggly plus V2 bar minus V2 squiggly. Okay? And so, if this thing up here was equation 1, I'll call this equation 2. And then what we could do is we could combine equations 1 and 2 to get rid of V2 minus V2 squiggly. Okay? And so by doing that, what we get is V mix squiggly is equal to V1 bar minus V1 squiggly plus x2 d delta V mix dx2 at constant x1. Okay. All right, and so we have this equation here. It's a somewhat interesting looking equation. But why did I write it in this form? Okay. Now the reason I wrote it in this form is because, once again, we're trying to determine what V1 bar and V2 bar are from data. And if we take a look at the form of this equation, you'll notice that if our independent variable is x2 and our dependent variable is this delta V mix, which is what we measure, what we have here is a linear equation, right? Or a slope equation. So this is the independent variable. And then here, this derivative, that's describing a slope. And then this thing here, this is describing an intercept. Y-intercept at x2 is equal to 0. Okay? And so that's essentially what this equation is telling us. Right? And so how do we utilize this equation? Okay, so if we go and take a look at another plot from the textbook, it actually kind of shows us how we would apply this equation. And so we're looking at a mixture of water and methanol, and the delta V as a function of the mole fraction of water. Okay, and so in this case, I believe mole fraction of water is going to correspond to component A. Okay? All right, and so let's say we looked at a delta V value at 0.5, okay? And we wanted to figure out what the partial molar quantity of the water is and what the partial molar quantity of the methanol is, okay? And so at that data point, we would not only use the value of delta V mix, but we would also look at what the instantaneous slope is of that delta V mix as well, right? And so that's known as constructing a tangent line, okay? And so based on that slope and that value of delta V, you could construct a line that looks like this, right? That touches the curve in one spot, right? And so if we go back to our equation, once we have the slope at that part of the line, right, and we know the x2 value, and we know the delta V mix value, knowing those things, we could determine what the y-intercept of our line is. And once we have the y-intercept, so on this plot, it would be this thing right here. Once we know the y-intercept value, we know that that y-intercept value is just equal to the partial molar quantity V1 times the pure molar volume of species 1 as well. This is something, this value right here is something that we could just look up. And so if we have that value, then we could determine our partial molar volume like that. All right, and so that's at the y-intercept where x2, or your x value, is equal to 0. If you went to the other extreme, here, this, where x is equal to 1, that would correspond to the case. That intercept would correspond to V2 minus V2. So y-intercept at x2 is equal to 1 correspond to V2 bar minus V2. All right, and once again, oh, it's squiggly. Once again, you can look this value up, and so if you can measure this y-intercept and you can look this value up, that would allow you to get V2 bar. Okay? All right, and so this is at least just a description of the graphical method for measuring the partial molar volumes. In class, we're going to go through an actual example to do this.